So dear students, in our last lecture, we studied about RS system of nomenclature, which is more referred to as absolute system of nomenclature. So the absolute system describes the configuration, okay? And now today we are going to study, on this video, we are going to study about DL system of nomenclature. DL system of nomenclature is also referred as relative configuration method. Okay, so before studying DL, we have to first understand and revise again the concept of configuration. We must know what configuration is. So configuration means arrangement of atoms or group of atoms which characterizes stereoisomer, a particular stereoisomer, a particular stereoisomer is called its configuration, is called its configuration. So the definition of configuration is the arrangement of atoms or group of atoms which characterizes a particular stereoisomer is called its configuration. So let us understand this by taking an example. Say for example, this carbon is attached with a hydrogen and OH, and now there is a bromine atom coming out of the plane, and there is also a chlorine atom going inside the plane. This is one stereoisomer, and the other stereoisomer, its enantiomer is like this. Bromine is out of the plane, bromine is out of the plane, okay, and chlorine is below the plane. Now you can see that the first one is one isomer and the second one is another isomer. So these are two stereoisomers of each other. Obviously, they too will have a different configuration. How? Let us see the Fisher configuration of A. When we see the Fisher configuration of A, we will see that H and OH are on the vertical side, okay, and bromine will be on the left hand side and Cl will be on the right hand side. Whereas if we check out on B, we will see that H and OH are vertical, but bromine is on the right hand side and chlorine is on the left hand side. As you can see that the molecular formula of these two are same, structural formula is same, but the configuration of atoms are different, the arrangement of atoms are different. In the first molecule, bromine is on the left and Cl is on the right, but in the second isomer, chlorine is on the left and bromine is on the right. So these two isomers have different configuration. So we need to identify them and assign them a configuration. So that is why first we need to learn what configuration is. So configuration is the arrangement of atoms or group of atoms which characterizes a particular stereoisomer. And now you know that the position of chlorine and bromine on these two define or characterize a particular stereoisomer. So this is configuration. So in short, if you want to say what configuration is, its configuration is simply the arrangement of atoms in 3D space. Okay, it is simply the arrangement of atoms or groups in 3D space. So this is what configuration is. Now, I have already told you in the previous video that there are ways to describe the configuration. Okay, so there are ways to describe the configuration of a molecule. There are ways to describe the configuration of a molecule. Now, how can you describe the configuration of molecule? First of all, there has to be an absolute way, which is known as absolute configuration. Okay, and the second is relative configuration. Relative configuration. Okay, now we all must know that what these two means. So by the term absolute configuration, we mean actual we mean the actual arrangement we mean the actual arrangement of atoms or group of atoms in a particular stereoisomer. Okay, so absolute configuration gives you the actual arrangement of atoms, but they are actually uh, in the 3D space. Just for example, let us take this A and B as our example. As you have seen that in A, H and OH were vertical, bromine was on the left hand side, chlorine was on the right hand side. So, I have already told you the way of presenting absolute configuration is RS nomenclature. Okay, so we will now do what? We will see this RS configuration, as because it is absolute configuration, it will tell us how actually these atoms are arranged. Okay, so this is HOH, Cl on the left hand side and bromine on the right hand side. Now, as you can see, first priority will be given to bromine because it is having the highest atomic number. Then second priority will be given to chlorine, third priority will be given to OH, and fourth priority will be given to H. In the same way here, first priority will be given to bromine, second priority to the chlorine, third priority to the OH, and fourth priority to the H. Now you see, if you go from 1, 2, and 3, you are going in the clockwise direction. That means this molecule is having R configuration. Whereas if you will go here from 1, 2, 3, you will go anti-clockwise direction and you will have S configuration. So this R and S configuration will give you how these nomenclature or these configurational system are based on how actually they are arranged on the space. We are not representing the configuration with respect to any other previously defined configuration. So this is what absolute configuration means. So we have already discussed RS configuration, that means the absolute configuration, in our previous lecture. Now today our main video or main lecture is on the relative configuration. So first of all, the relative configuration actually means the arrangement of atoms or group of atoms in space of a stereoisomer of a compound relative to the atoms or groups of atoms of of another compound chosen as chosen as arbitrary standard. Now, this is a very important thing. Okay, you should understand what relative configuration means. So, relative configuration means arrangement of atoms or group of atoms in a space of a stereoisomer, obviously, of a compound relative to the atoms or group of atoms of another compound. Means we are not actually presenting the configuration on the basis of how actually the atoms are present, but on the other hand we are presenting configuration with respect to some another compound which has been chosen as an arbitrary standard. So there is a standard. Okay, so let me give you let me make you understand in a shorter way that we are having a standard compound. It would be having some kind of configuration, and its configuration is known to you. Now, somehow your compound is related to this. Your compound is related to this standard, and the configuration of this standard is assigned to your compound. Okay, so this configuration, because your compound is related to this standard, so your compound is having the same configuration as that compound. So this is how relative configuration works. Okay, so whatever our compound is, we will see whether it is whether our compound is related to the standard or not. If it is related to that standard, or whichever the standard, its configuration is assigned to the compound. Okay, so the configuration of this compound is just assigned on the basis of a standard. So it means that it does not represent the actual arrangement of atoms or groups within our molecule. Okay, so now let us see what these standards are. Okay, so let us see an example of lactic acid. Let us see, we are having lactic acid. Lactic acid, the structure of lactic acid, if you draw it in Fisher way, so its structure is like this: OH, CH3, and its isomer can be written as OH, H, COOH, and CH3. So this is our lactic acid. Okay, this one is our enantiomer number 1. These two are optical isomers. This is our enantiomer number 1, and the second one is our enantiomer number 2. So they are having different configuration around the chiral center, as you can see it well, because OH is on the right hand side in the first, whereas OH is in the left hand side in the second. Okay, so now one of these will be dextrorotatory and one of these will be levorotatory. Now, how do we know? The question arises, how do we know which one is, you know, dextro, which one is representing dextro, and which one is representing levo, like this? So we want to know this. Okay, so now for this, we have arrived to our relative configuration method. So in the DL system of nomenclature, okay, so in the DL system of nomenclature, DL system, we take glyceraldehyde as a standard. Okay, we take glyceraldehyde as our standard. Now, what is the structure of glyceraldehyde? The structure of glyceraldehyde is like this. They have chosen that obviously glyceraldehyde is having structure like this: CH2OH, and this is OH, and this is H. Now, first of all, in this standard, we have chosen that the glyceraldehyde which is dextrorotatory, dextrorotatory, that means plus, which is plus. While writing the Fisher configuration of it, its OH group will be written on right hand side, while the glyceraldehyde which is levorotatory, which is minus, its OH will be written on the left hand side. First of all, we have assumed this. And the one which is dextrorotatory is given the name capital D, and levorotatory will was given the name, was assigned the configuration capital L. Now we have arbitrarily chosen it. So on this OH, as because it is D and it is dextrorotatory, it is D glyceraldehyde. Okay, so there is another glyceraldehyde which is levorotatory, OH on the left hand side and H on the right hand side. CHO, this is L, this is negative glyceraldehyde. So this is negative. So we are having dextroglyceraldehyde and levoglyceraldehyde. Now it has been assigned that the dextroglyceraldehyde or the D-glyceraldehyde, its OH will be always written on the right hand side, whereas the levoglyceraldehyde, its OH will be written on the left hand side. So this thing we have fixed on it. Okay. Now we have defined one thing, and it is now how will we establish a configuration. So configuration established as any compound. Okay, listen carefully. Any compound that can be prepared from that can be prepared from or converted into D plus glyceraldehyde. D plus glyceraldehyde will belong to D series, will belong to D series. Okay, and similarly any compound that can be prepared from prepared from or converted into L minus glyceraldehyde will belong to L series, will belong to L series. Now what does that mean? For example, we are having glyceraldehyde. Okay, we are having CHO single bond like this OH, H and CH2H. We are having glyceraldehyde. So this is our D-glyceraldehyde having being dextrorotatory. Okay, now we do a chemical reaction. We reacted with bromine, Br2 and water, and we perform the oxidation. Now due to oxidation, the aldehyde group of this glyceraldehyde is converted to COOH, and rest of the groups remain same. Now we have converted this to a new molecule called glyceric acid. We have converted into glyceric acid. Now what will be the configuration of glyceric acid as per the configuration? So its configuration will be D. It is assigned as D because it is prepared from D-glyceraldehyde. So the configuration assigned to it will be D because it comes in D series. Now, whether it would be dextrorotatory or levorotatory, see, the glyceraldehyde over the glyceric acid over here is actually levorotatory. So, what we have understood is D and L, okay, D and L are simply relative configuration, and the configuration means simply means how you can represent a isomer or a stereoisomer on a paper. Okay, how will you represent them? How will you say that this one, this, how will you characterize the isomer? How can you write it on a paper? So this is the way. In the same way, the RS configuration that we have studied, which was absolute configuration, it also tells about the isomer. It represents the isomer. It also tells us how the isomer is arranged, how you can write it on the paper. But the difference is that this RS gives the actual representation, how they are arranged. You can write it on the paper. But DL, on the other hand, gives the configuration relative to diglyceride. It does not tell us actually where they are arranged. But you know, the thing is that how can we identify whether an isomer is dextro, if it is D, whether it is dextro or levo? No. If a molecule is obtained from D-glyceraldehyde, which is dextrorotatory, and obviously its family will be D, but you don't know whether it is dextrorotatory or levorotatory. It may be levorotatory afterwards, or it may also be dextrorotatory. Like as that in case of glyceric acid, you have seen that glyceric acid is although of D, so don't think that D, capital D means dextrorotatory. Capital D and capital L simply represents the relative configuration or the configuration of the isomer relative to D-glyceraldehyde. It does not mean dextrorotatory. Always remember, if a compound is dextrorotatory, it is represented by small d, and levorotatory, it is represented by small l or minus, small d or plus dextrorotatory, small l or minus levorotatory. But capital D, capital N means it simply gives the relative configuration with respect to glyceraldehyde. Okay, now let us take one more example similarly of L-glyceraldehyde. Say we are having L-glyceraldehyde, and okay, and you know that in L-glyceraldehyde we are having OH on the left hand side. It has to be represented on the left hand side. Okay, CHO and CH2OH. So we are having L-glyceraldehyde, and we already know that L-glyceraldehyde is levorotatory. Okay, this is L-glyceraldehyde. Now, what will happen that we will react it with bromine Br2H2O, as we did with D-glyceraldehyde. We perform the oxidation. Now, what will happen is that COOH, okay, it's COOH, the CHO group will be converted into COOH, OH on the left hand side, H on the right hand side, and CH2OH. Now, as you know that this thing has been obtained from L-glyceraldehyde, so the relative configuration will be L. Now, what about is it dextrorotatory or levorotatory? The answer is that this compound is levorotatory. Okay, this glyceric acid is levorotatory. But when you treat this glyceric acid with phosphorus tribromide PbR3, you get another compound COH. You will it will undergo bromination. You get CS2Br. Obviously, the family will be L, the series will be L, the relative configuration will be L, but this compound is now dextrorotatory. Okay, now when you treat this compound with zinc in presence of acidic environment, you get OH, H, COOH, and CH3. Now you get lactic acid, and this lactic acid obviously would belong to the L family, but this lactic acid is dextrorotatory. Now you see that L, capital L and capital D already represents that our molecule is obtained from L-glyceraldehyde, and whenever you write its OH on the paper, it will be always written on the left hand side. And in the dextrorotate, if it is D of capital D configuration, its OH will be written always on the right hand side. Okay. Similarly, please remember that even in RS configuration, we don't know whether our compound is dextrorotatory or levorotatory. There is only one way to check it out. You have to put it into the polarimeter and check whether the compound is dextrorotatory or levorotatory. You can only see with RS or DL that how the atoms are arranged in the 3D space, and it will be easier to write on the paper. Now, what if, you may ask, what if we are having more than one OH group in the molecule? Okay, like for example in carbohydrate chemistry. Let us see this glucose. Let us take example of glucose. Glucose is CHO, okay, and it's HCOH, then OHCH, then HCOH, then HCOH, then CH2OH. Okay. Now this compound over here, okay, this compound over here that you can see here is actually belongs to the D family, capital D. This D-glucose is obtained from D-glyceraldehyde. And if we say whether it is dextrorotatory or levorotatory, so I am telling you that this is dextrorotatory, this is D-glucose. Now, which OH represents capital D? Obviously, you know that the OH in capital D should be on the right hand side. Now, which OH it is? So, is it the OH of the second carbon? Is it the OH of is it OH of the fourth carbon, or is it OH of the fifth carbon? So let me tell you that actually it is the OH of the fifth carbon. Why? Because see, the real glyceraldehyde is this one, the D-glyceraldehyde, D-dextro plus glyceraldehyde. It is this. Now, the OH that we take in glyceraldehyde is just the penultimate carbon. That means the carbon just before the last carbon. Okay, and always remember that the highest oxidized carbon is should be on the top. So the penultimate carbon you have to check, and obviously it's OH on the right hand side. That is why it is D-glucose. Okay. Now, if you do the mirror image, okay, now if you take the mirror image of this D glucose, you will see that the L glucose should have its OH on the L series should have a OH on the uh, so let's see, this is mirror. So in this case, our OH of the L series will be on the left hand side. So you see that this OH on the left hand side, this is H. Now this is HOH. Now this one is OH, H, and this one is then OH and H, and this is CH2OH. Now as you see that penultimate carbon has to be taken into account, and its OH lies on the right and left hand side. Hence this one belongs to capital L series, and you remember that capital L glucose is levorotatory. Okay, so this is how we do the configuration of DL configuration of the uh, carbohydrate glucose. So not only DL, but in the carbohydrates or in the um, other other compounds, this configuration is not limited to them. It can also be applied to the amino acids. Okay, so in amino acids we can also give them D or L configuration. Okay, like for example, in this L configuration, it's basically the NH2 which is related. For example, CHO, OH, H, and CH2H. Now you know that this one is our L glyceraldehyde. Okay. Uh, and in amino acid, we don't have OH group. Okay, you know that we don't have OH group. So we have NH2 group. So you can see that this NH2 group is on the left hand side and this belongs to the L. Okay. So this belongs to the L. So this is how D and L configuration is decided. Okay. And there are some limitations as well. Limitations of DL configuration. You must know this thing as well. First of all, this method is quite cumbersome. Okay. So it is not good for those compound having two or more chiral atoms, chiral carbon atoms. It is not. It would become very a little difficult. Okay, and a better way is to give the actual configuration, which is given by RS configuration. So, dear student, this is all about DL configuration, the relative configuration. I hope you have understood the basic concept underlying it. So, this is all about the topic. Now, let us move on and meet on the next video. Thank you.